Welcome to the third stage of the Trivium, Rhetoric. My name is Alex Craig, and I'd like to begin by posing what might seem like a simple question. What is math? Now, perhaps you would just say math is annoying, and would be quite content with leaving it there. But if you really try hard to think about it, math is actually quite hard to define. Our math curriculum at Rockbridge has three major themes, which can be seen as possible answers to this question. The first is that math is God's invention and only man's discovery. I think this is important for two major reasons. The first is that it gives us an objective, absolute basis for math. Now, if I were a materialist, meaning that I didn't believe in the existence of anything except physical matter, then I would be inconsistent in treating math as anything other than a set of rules, which, in my experience, the universe tends to follow. And so I could not treat math as any sort of abstract thing apart from the physical universe. However, as Christians, we can believe that God created math independent from the physical universe, and so we can treat that creation as our objective standard. This is also important because it explains why math models the physical universe so well. It's because God created both of them, and He created the physical universe in such a way that it would be modeled by His other creation, math. The second theme is that math is a language. Just like any language, we can express meaningful ideas in the math language. For example, we could say a equals pi r squared, which means that the area of any circle equals pi times the radius squared. We also talk about this in science class because math is the language of science. This means that if we have a science problem, we are going to express our solution using the math language. Finally, we talk about math modeling. This means that we can use the language of math to model real-world phenomena. For example, we already talked about how we can use a formula for the area of a circle, which is math language, to model the area of a circle. We can do the same thing with side lengths of a right triangle using the Pythagorean theorem. Or we could model the temperature of a cooling object using Newton's law of cooling, which is in math language. I'm going to do an example problem for you in which we model a real-world situation inside of a pipe using math language. The problem states, a pipe has an inner diameter of 20 centimeters. Over time, mineral deposits form a coating on the inside of the pipe, reducing the area through which fluid can flow. If the area of the pipe has decreased by 19%, how thick is the coating of mineral deposits? The first thing we're going to do when we approach this problem is to write down what the question is asking. In this situation, the question is asking for the thickness of the mineral coating. So we write that down. This will hopefully help us from doing a lot of work and accidentally solving for the wrong thing and getting the problem wrong. We've also drawn a preliminary diagram that can help us start to think about what the problem is asking. So we have a pipe, and we take away a small mineral coating, and we're going to have a certain amount left over. And the inner diameter of the pipe is 20 centimeters. The next step is to prepare to write an equation. We'll assign the variable name x to be the thickness of the mineral coating. And since that's what the problem is asking for, if we solve an equation, we'll be solving for x. Since the problem is talking about pipes, and pipes are normally circles, we'll probably need to know the formula for the area of a circle, which is a equals pi r squared. Since this formula is in terms of r, the radius, instead of the diameter, we'll need to know the radii of the circles in the problem. The most obvious circle in the problem is the pipe, and we already knew that the pipe had a diameter of 20 centimeters, and so we can find the radius is half of the diameter is 10 centimeters. The other circle in the problem is the remaining circle once we've taken away the mineral coating. The radius of that will be 10 centimeters, which is the radius of the total pipe, minus the thickness of that mineral coating. So it will be 10 centimeters minus x. The next thing we'll do is find the areas of those circles that we talked about, since we already found their radii. We can just plug the radius into the formula for the area of a circle to get the total area of the pipe, pi times 10 centimeters squared. And we can do the same thing for the area of the remaining circle once we've taken away the mineral coating. And that will be pi times 10 centimeters minus x squared. Now we can fill in more information in our diagram to make it more helpful. So we already knew that the total diameter was 20 centimeters, and from that we determined that the radius must be 10 centimeters. We defined x as the thickness of the mineral coating, and we said that 10 centimeters minus x was the radius of the remaining circle. Now we have to deal with the part of the problem that talks about percents. The problem said that the area of the pipe decreased by 19% when we took away that mineral coating. And so that means that the mineral coating must have accounted for 19% of the total area of the pipe, which means that 81% must remain, since 81 plus 19 equals 100. If we think about the nature of a percent, this means that if we form a fraction with the area of the remaining circle over the total area of the pipe, that must equal 81 over 100, which is just another way of writing 81%. So we can actually form a preliminary equation using that information. And now it becomes clear why we figured out the areas of those circles. Now we can just plug them into that equation and get the equation that we'll actually solve. It's pi times 10 centimeters minus x squared over pi times 10 centimeters squared equals 81 over 100. Now we actually have to get down to the grunt work of solving this equation, and so we'll write it at the beginning of a new slide, and we can work down from there. The first thing we'll notice is that we have a pi in the numerator and a pi in the denominator on the left side of the equation. And so these will form a multiplicative identity, and we don't have to worry about them anymore. The next step is that each remaining piece of the equation is a perfect square. And so if we take square roots of both sides of the equation, that should simplify things for us. However, we have to remember that the square root of a positive number can be either positive or negative. So we have to include this pesky plus or minus sign there. Now we can actually simplify this to get 10 centimeters minus x over 10 centimeters equals plus or minus 9/10. Now we have an equation of fractions, and so we'll cross multiply to simplify. We'll get 10 times 10 centimeters minus x equals 10 centimeters times plus or minus 9. Now we have to rewrite that at the beginning of the other side so we can work down from there. Using the distributive property, we can multiply out the left side to get 100 centimeters minus 10x equals plus or minus 90 centimeters. Now each piece of our equation is divisible by 10, and so if we put both sides over 10, that should simplify things for us. 100 centimeters minus 10x over 10 is 10 centimeters minus x, and 90 centimeters over 10 is 9 centimeters. So we get 10 centimeters minus x equals plus or minus 9 centimeters. Now we have our variable x without any coefficient on it, and so our next step will try to get x to its own side of the equation. We're subtracting x from the left side of the equation, and so we'll need to add it to get it over to the right. But on the right side of our equation, we have the plus or minus 9 centimeters, and so we'll need to move that over to the left side of the equation. So this next step looks complicated, but all we're doing is adding x minus or plus 9 centimeters to both sides of the equation. On the left side, this minus x and this plus x will form an additive identity and will disappear. And on the right side of the equation, the plus or minus 9 centimeters and the minus or plus 9 centimeters will also form an additive identity and they will disappear. So we'll be left with 10 centimeters minus or plus 9 centimeters equals x. And since it's more customary to write the variable on the left side of the equation, we'll rewrite it and get x equals 10 centimeters minus or plus 9 centimeters. We can't go any farther without actually dealing with that pesky minus or plus sign. So if we think about what that's really saying, it's saying that x could equal 10 centimeters minus 9 centimeters, or x equals 10 centimeters plus 9 centimeters. So if we go back and think about what x was really talking about, x was the thickness of the mineral coating on the inside of the pipe. So our math solution is telling us that the thickness could either be 1 centimeter or it could be 19 centimeters. So the 1 centimeter solution makes sense. We have a 20 centimeter pipe and a 1 centimeter coating would just be thin around the inside. But a 19 centimeter solution, or a 19 centimeter thick coating, would actually have to pass through itself on the inside of the pipe. And since things in our physical world can't pass through themselves, we say that doesn't make sense, and we call it an extraneous root. The only solution that does make sense is 1 centimeter, and so that's our solution to the problem. This is just one example of how rhetoric can be used in the third stage of the Trivium. Thank you.